Hello everyone, welcome to Civil Galaxy. Myself Dr. Pruthviraj B S. In today's session we shall see how to analyze a continuous beam using Kanis method. So for that I have considered here a simple problem where span AB is carrying an UDL of 20 kN per meter and span BC is having an eccentric loading of 50 kN and span CD is carrying an UDL of 20 kN per meter. So in Kanis method the first step will be to find or to calculate the fixed end moments. The fixed end moments, that is FEM. So if we take or consider the span AB here, we need to find out the fixed end moment for span AB first. Since it is having a UDL here, the formula will be minus WL square upon 12. W here is 20, so minus 20, and the span here is 6 meters, so 6 square upon 12, which will be equal to minus 60 kilonewton meters. Similarly, now we have to find out the other side of the span, that is fixed moment about point B to A will be equal to, the formula remains same, just the sign changes, which is plus WL square upon 12. W here is 20 into span is 6 meters upon 12, which will be equal to plus 60 kilonewton meters. Similarly, we have to find out the fixed end moment for span BC, since it is having an eccentric loading here at a distance of 3 meters from point B here. So the formula will be minus WA B square upon L square, which will be equal to W is 50, A this distance from point B, that is 3, into B here is 2 meters, so B square will be 2 square upon the total span or the total length, which is 5 square, which will be equal to minus 24 kilonewton meters. Similarly, we have to find out the fixed end moment from point C to B. The formula is plus W A square B upon L square. W here is 50, so plus 50 into the distance A is 3, so 3 square into B is 2 upon the total span here is 5 square. So the answer will be plus 36 kilonewton meters. Similarly, we need to find out the fixed end moment for span C to D. So since span CD is carrying an UDL of, a load of UDL intensity 20 kN per meter, the formula will be minus W L square upon 12. W is 20, so minus 20. The total span is 4 upon 12, which gives an value of minus 26.67 kilonewton meters. Similarly, for fixed moment from point D to C, which will be equal to plus W L square upon 12. W here is 20. The total length is 4 meters upon 12. The answer will be plus 26.67 kilonewton meters. So if we just observe the beam here, At point A, we are having a fixed support, and at point D, we are having a simple support. So, whenever we are having a support which is other than fixed support, we need to go for the modification of the fixed end moment. So, if we go for modification for span CD, that is A is fixed support here and D is a simple support here, and we know that whenever we are having a support other than the fixed support, maybe it is a simple support or hinge support or roller support, the final end moment at this point should be equal to 0. So the fixed end moment from point D to C, we have got a value of plus 26.67, which means we have to take an additional moment so that we can make this final end moment as 0. So MFDC, that is the fixed end moment about point DC, was how much here? We have taken the value, that is plus 26.67 kilonewton meter. Now if we have to make this final end moment about this point as 0, that means I have to apply equal and opposite moment to make the value as 0. So that is M dash FDC, this is the modified fixed end moment, will be equal to the value we have got is plus 26.67, adding equal and opposite, so subtracting it by the equal and opposite moment, that is minus 26.67, which will be equal to 0. Now after getting the value or after making the final end moment value as 0 here, from moment distribution method, we have learnt that whatever the extra or the additional moment we have considered here, half of that value has to be carried to the other side of the to the other end of the same member here. So if I want to modify, that is M dash FCD, the value here we have got is this one, minus 26.67 plus half into the modified value. Now what is the modified value we have taken here? That is minus 26.67. So the modified value of the fixed end moment about point CD will be equal to minus 40 kilonewton meters. So here the next step will be to calculate the relative stiffness and the rotation factor. So for that I have taken or considered here a table where I have to consider the joint and the member pertaining to that particular joint. So if we observe the beam here, we are having two joints, that is B and C. So if I consider joint B here, so B is connecting from B to A also and from B to C also. So we are having two members, that is B to A and B to C. Similarly, if we consider the joint C here, at C we are having two members, that is C to B and C to D. So now I have to consider I have to find out the relative stiffness for that particular member. So whenever I need to find out the relative stiffness for that particular member, we have to see or consider the far end conditions. See, if I take the span, that is member BA here, B is the near end and A is the far end. So B is the near end and A is the far end. So if I observe the conditions at the far end, A is fixed here. So whenever we are having a fixed support, the stiffness will be equal to I by L. I they have not given, so we will take it as uniform. So I by L, the total length here is 6 meters, which will be equal to I by 6. The value will be equal to 0.17 I. Similarly, for span BC here or member BC, from B to C, B is the near end here and C is the far end. Since C is an intermediate support, in structural analysis, we consider the intermediate support also to be an fixed support. So, the member BC here, since C is considered as a far end and it is considered as a fixed support, the stiffness will be equal to I by L. I divided by the total length here is 5 meters, which will be equal to the value 0.2 I. Now, if we add the totals, the stiffness of these two members, I am going to get the total stiffness for joint B, that is 0.5 I, 0.17 plus 0.2 I, which will be equal to 0.5 I. Similarly, for joint C here, I have to take the stiffness for member CB. C is the near end and B is the far end. Since B also is an intermediate support here and intermediate support is considered as a fixed support, so the value will be equal to I by L. So the value will be I by 5, which is equal to 0.2 I. Now, if we consider from C to D, C is the near end and D is the far end. Since the far end is a simple support, whenever there is an support other than the fixed support, maybe it is a simple support, roller support or hinge support, we consider only 75%. For if it is a fixed support, we are taking it as 100%. If it is having a support other than fixed support, maybe it is a simple support, roller support or hinge support, we are taking only 75%, which will be equal to 3 by 4 into I by L. That is 3 by 4 into I by, the length here is 4 meters, which will be equal to 0.19 I. So if I add these two stiffness, I am going to get the total stiffness, that is 0.39 I. So now I need to find out the rotation factor, which is given by U is equal to minus half into K by sigma K. That is nothing but minus half into this K by sigma K is taken as the distribution factor. So if I just put the values here, my final answer will be for member BA minus 0.23 and here will be equal to minus 0.27 and for member CB it is minus 0.26 and for member CD it is minus 0.24. So the next step here is to calculate the Kanis table or the rotation contribution table. So what we have done here is we have replaced the intermediate support with the help of the boxes here. This is point A and this is point B, this is point C and this is point D. So whatever the values or the fixed end moment we have got in the first step, we have to write here. That is fixed end moment from A to B and from B to A, similarly from B to C, C to B, C to D and D to C. So what is the fixed end moment we have got here in the first step? It was minus 60. I'll write only the values, not the units here. From B to A, the fixed end moment was plus 60 and from B to C, the value was minus 24. The fixed end moment from C to B was plus 36 and from C to D, we have to write the modified fixed end moment, that is minus 40 and since D is a simple support here, the fixed end moment or the modified fixed end moment here was 0. So now in this place here, this place, we have to write the rotation factor which we have got in the step 2. So For member B to A, the rotation factor we had got is minus 0.23, and here from B to C it was minus 0.27. Similarly, from C to B, the rotation factor was minus 0.26, and from C to D, the rotation factor was minus 0.24. See, if we observe here, I need to find the rotation contribution, that is, I will take it as M dash AB. Here, this will be M dash BA. Here, M dash BC. This will be M dash CB. This is M dash CD. This M dash DC. Since the rotation contribution we are calculating here only for the intermediate supports, M dash AB will be equal to 0 and M dash DC will be equal to 0. So if we need to calculate the rotation contribution about this point, say M dash BA, the rotation contribution, the formula we know, which is given by U into summation of fixed end moment plus summation of far end rotation contribution. Far end rotation contribution. Say, for example, now if I want to calculate about point B, which is the far end here, the far end will be M dash AB. That means I have to consider this value here. Similarly, the far end rotation contribution here will be M dash CB. That means I have to calculate or consider this value. If I come for C here, the far end here will be M dash DC. I have to take this value into consideration, and M dash BC will be the far end. So I have to take or consider this value here. So if I go for the first iteration here, considering the first M dash BA, that is the formula we know here, U, that is the value here from B to A, M dash BA, it is minus 0.23 into the summation of fixed end moment here. The summation of fixed end moment means what we have got the value, that is fixed end moment from B to A and from B to C, this values minus plus 60 and minus 24. These two value, the summation we have to write here in this box, which will be equal to here 36 plus 60 minus 24. Here plus 36 and minus 40 will be equal to minus 4. So this value we need to consider here, that is, so minus 0.23 into the value here is how much? Fixed end moment, summation of fixed end moment is 36 plus summation of far end rotation contribution. About this point, the far end rotation contribution here is M dash AB, the value is 0, and M dash CB, the value we don't know, so we will consider it as 0. So the value will be equal to minus 8.28 kilonewton meter. Similarly, for M dash BC, U is minus 0.27, fixed end moment value remains same, plus 0, which will be equal to minus 9.27 kilonewton meter. So now this value, that is M dash BA, this value we will consider here is minus 8.28. Similarly, this value M dash BC we will consider here minus 9.27. So next we will go for M dash CB. The rotation factor here is minus 0.26 and the summation of fixed end moment value is minus 4 plus what is the far end rotation contribution here, that is the value, the new iteration value is minus 9.27 plus 0, because the far end rotation contribution, that is m dash dc, is 0. The value will be equal to 3.56 kilonewton meter. So this value we will write here plus 3.56. Similarly, m dash cd so if we consider similarly m dash cd will be equal to, the rotation factor here is minus 0.24 into summation of fixed end moment, that is minus 4, and this value, the far end rotation contribution, minus 9.27 plus 0. The value will be equal to plus 3.29 kilonewton meters. So the value here is plus 3.29. So we have to go on doing the iteration process until and unless the values here seems to be similar. So if we go for the second cycle here, if you go for the second cycle, the values here remains same, only this iteration process values will keep on changing. The new iteration values or the new far end rotation contributions keep on changing, rest everything remains unaltered. So for the second cycle, if you consider here, that is u minus 0.23, summation of fixed end moment 36, plus the new iteration value or the new far end rotation contribution here is how much? Plus 3.56 plus 0, that is this value, which will be equal to minus 9.09 kilonewton meters. Similarly here 3.56 plus 0 will be equal to minus 10.68 kilonewton meters. So the value we have to write here minus 9.09 minus 10.68. So if we observe here, the values are not similar, which means the iteration process needs to be continued. So if we come for m dash cb here, the value will be the new iteration value or the new far end rotation contribution here is minus 10.68 plus 0. The value will be equal to plus 3.81 kilonewton meter. We'll write here plus 3.81. Similarly here, the new iteration value here is 10.68 plus 0. The value is plus 3.52 kilonewton meters. So plus 3.52 kilonewton meter. So since the values are not similar here, again we'll go for a third cycle. Everything remains same, only the values, the new iteration value or the new far end rotation contribution changes. So what is the new iteration value here, m dash ba? If I consider, this is the new value here is plus 3.81 plus 0, which will be equal to minus 9.15 kilonewton meter, that is minus 9.15. Here it is 3.81 plus 0, which will be equal to minus 10.74 kilonewton meters. So here the value we have to write here, that is minus 10.74. So the new iteration value here we have got is minus 10.74. This will add here 10.74 plus 0, which will be equal to plus 3.83 kilonewton meters. So here we'll add it plus 3.83. Similarly here minus 10.74 plus 0, which will be equal to plus 3.53 kilonewton meters. So this value will add here plus 3.53. So since the values are still not same here, we'll go for another cycle. This was cycle 3. Now this is cycle 4. So just we have to change the values here for new iteration values or new far end rotation contribution values, which will be, see here, plus 36, that is this value fixed end moment, plus the far end rotation contribution. How much here is the new value? That is plus 3.83 plus 0, which will be equal to minus 9.16 kilonewton meters. So we will write here minus 9.16. So similarly for M dash BC, the new value here, the new iteration value is plus 3.83 plus 0. The value will be minus 10.75 kilonewton meters. So here this will be minus 10.75. So here taking the new iteration value, that is minus 10.75 plus 0, which will be equal to plus 3.83 kilonewton meters. So we'll add the values here, plus 3.83, and for M dash CD, it is minus 10.75 plus 0. The value is plus 3.54 kilonewton meter. This will take here 3.54. So we can see almost the values are similar here. So maybe in the fifth cycle, we are going to get the similar values. So taking the fifth cycle, where the values so here it is the new iteration value, that is 3.83 plus 0, which will be equal to minus 9.16 kilonewton meter. Similarly here 3.83 plus 0, the value is minus 10.75 kilonewton meter. So the value will add here minus 10.75. So here minus 4. So minus 4, and the new value, new iteration value here is minus 10.75 plus 0. The value will be equal to 3.83 kilonewton meter. So plus 3.83 kilonewton meters. Similarly for M dash CD, that is minus 0.24 into summation of fixed end moment is minus 4 minus 10.75 plus 0, the value will be equal to plus 3.54 kilonewton meter. So we will write here 3.54. So if we just observe now, we have got the values similar, minus 9.16 in the fifth cycle also it is minus 9.16, here it is 10.75, 3.83 and 3.54. So now we can stop the iteration process here. See here. So this value we will take it as m dash BA and here m dash BC, here m dash CB and lastly here m dash CD. So my next step here, this was step 3. This was step 3 here. So my next step in step 4, the last step will be to calculate the final end moments. So to calculate the final end moments, if I take moment about A to B, the formula here is fixed end moment about that point, that is A to B, plus 2 times of rotation contribution about the near end plus 1 times the rotation contribution about the far end. So if I add the value here, that is fixed end moment about point A to B is minus 60 plus 2, the rotation contribution about the near end, how much here it is? 0, plus 1 times the rotation contribution about the far end, that is minus 9.16, which will be equal to minus 69.18 kilonewton meters. So this is the value. Similarly, if I take for final end moment from point B to A, the formula is fixed end moment from point B to A plus 2 times the rotation contribution about the near end plus 1 times the rotation contribution about the far end. So here the fixed end moment value is how much? Plus 60, that is plus 2 into m dash BA, the value we have got here, that is minus 9.16 plus this value will be equal to 0. So the final end moment about point B to A will be equal to, that is plus 41.68 kilonewton meters. So this is the value. Similarly, if we calculate for the other members also, the value here is MBC we have got minus 41.68 kilonewton meters. Similarly, MCB, the value we have got here is plus 32.91 kilonewton meters. Similarly, MCD, for MCD, the fixed end moment, we should take the modified fixed end moment, will be equal to minus 32.91 kilonewton meters, and MDC already we have made it as 0. So MDC will be equal to 0. So this is how we calculate the final end moments. So now just adding the values here, that is the final end moment about point A to B here, if we write, that is minus 69.18 kilonewton meters. Similarly, about point B to A, the value here is in the clockwise direction plus 41.68 kilonewton meters. Similarly, for B to C, it is anti-clockwise here. The value is 41.68. From C to B, the value here is 32.91. 91. Here also it is 32.91. About D to C it is 0. So now if you want to calculate the support reactions and the maximum bending moment, we will consider it as step 5, that is to calculate support reactions and maximum bending moment. See, if we consider the span AB here, let us consider the span AB, it is the free body diagram, which is having a UDL, and of intensity 20 kilonewton per meter over a span of 6 meters. This is B, this is A. Now we are having a anti-clockwise movement here, that is 61.18 kilonewton meter. Here at point B we are having a clockwise moment, that is 41.68. So now if I want to calculate, that is, I will take it as RAB and this as RBA. If I want to know the value of RAB and RBA, I will take summation of all the moments about point A equal to 0, about this point here, which will be about this point, means force multiplied by perpendicular distance rotating in the clockwise direction will be positive, that is RBA into, rotating in the anti-clockwise will be negative, that is minus RBA into 6 about this point here. Here we are having a UDL which is coming downwards, rotating in the clockwise direction, which will be equal to plus 20 into the distance into CG, 6/2, since it is a UDL. And here I am having a anti-clockwise moment, that is minus 61.18 plus here a clockwise moment, that is 41.68, which will be equal to 0. So in this equation only one unknown value is there. So if we calculate, the RBA value will be equal to 55.42 kilonewtons, that is in the upward direction. So similarly now, if I take the condition, that is summation of all the vertical forces is equal to 0. I will take it as summation of all the forces in the y direction is equal to 0. Then this one here, RAB is going in the vertically upward direction, positive, plus RBA. Here the UDL is coming in the downward direction, that is minus 20 into 6, which will be equal to 0. RBA value we have got here. So if we calculate, RAB value will be equal to 64.58 kilonewton. This is also in the upward direction. So we have got RA and RB. So if I extend the line of action here, if we need to find out the maximum bending moment, since it is an UDL, we don't know at what point. So let us consider drawing the shear force diagram here. That is at point A here, if I calculate at RAB, it is 64 somewhere here. RAB, let us take it as 64.58, and since it is a UDL here, that is plus 64.58 minus 20 into 6, the value will be somewhere here, that is the value is minus 55.42, and now if we add this minus 55.42 plus 55.42 will be equal to 0 here. This is negative, this is positive. here. So we don't know, we just have calculated here the value. So excuse me, just a minute. I shall write one more time correctly. So here it will be probably like this here, yes. So this is negative here, this is positive here. So this point where the shear force is 0, we know that whenever the shear force is 0, the bending moment will be maximum at this point. So if we consider this point only here, that is somewhere here, let us consider this point as point E, and this distance as Ex. So this distance will be equal to, the total distance is 6 minus x. So now if we apply the properties of similar triangle, this distance upon the height here, that is x by 64.58, which will be equal to 6 minus x upon 55.42. So the value will be of x. The value of x is something 3.23 meters. So at a distance of 3.23 meters, we are getting the maximum bending moment. So now, if I want to find out the maximum bending moment about this point E, that is maximum bending moment at E, I have to consider either the left or right of the section. So considering the left of the section here, about point E here, we are having RAB at a distance of x, that is 3.23, rotating in the clockwise direction, that is RAB into 3.23, and we are having one anti-clockwise movement also here, it is minus 61.38, and about this point we are having a UDL which is rotating in the anti-clockwise direction, that is minus 20 into 3.23 into 3.23 divided by 2, since it is an UDL. So the maximum bending moment about point E will be equal to 35.10 kilonewton meters. So now similarly, if we take for span BC, if we consider the span BC, this is B, this is C. Since it is having a point load at a distance of 3 meters from point B, we can directly say that the maximum bending moment is under this point load, which is having a intensity of 50 kilonewton. This is 3 meters, this is 2 meters. Here we are having a clockwise movement of 32.91. Here we are having an anti-clockwise movement of is 41.68. So this we will take it as RBC, this as RCB. So now if I want to find out the value of RBC and RCB, we will consider summation of moment about point B is equal to 0 here about this point. So force multiplied by perpendicular distance rotating in the anti-clockwise direction negative minus RCB into the total distance is 5 here, 3 plus 2 5, plus 50 into the distance here 3, and anti-clockwise, that is minus 41.68 anti-clockwise moment plus the clockwise moment here 32.91, which will be equal to 0. So RCB value here will be equal to, that is 28 28.24 kilonewtons. Similarly, now if I consider summation of all the forces in the vertical direction to be equal to 0, that is RBC plus RCB minus 50 is equal to 0. RBC value we don't know, we need to find out. RCB value we have got. So if we just put the value and substitute, we are going to get the RBC value as plus 21.76 kilo Newton. So now if you want to find out, say this point, if you take it as point F, so the maximum bending moment about point F, we have to take either left or right of the section. We will take I will consider from the left of the section, which will be equal to here, that is RBC into 3 rotating in the clockwise direction, positive, and here it is minus 41.68 anti-clockwise moment. So the value will be equal to 23.61 kilonewton meters. So similarly, if I take for span CD, the same procedure what we have done for span AB will be taken into consideration, and that point we will call it as point G, where the maximum bending moment is occurring. So by considering that value, we can construct the shear force diagram and the bending moment diagram. So similarly, we shall see some other problems related to Kanis method in the next coming classes. Thank you.